below its melting temperature.
Polymer molecules that contain chlorine, oxygen, or nitrogen are called polar molecules. They have higher cohesive energies than nonpolar molecules such as polyethylene. However, because they are so large, all polymer molecules, whether polar or not, have reasonably high cohesive energies. These energies have a very important effect on many polymer properties, among them the melting point.
Polyethylene terephthalate, or PET, melts around 250 degrees Celsius. But long before that, at about 75 degrees Celsius, it reaches its glass transition temperature, Tg. At this point, the polymer becomes soft and flexible, almost rubbery. Now the forming begins. The sheet is clamped in place and pulled tightly over a mold using vacuum pressure, air pressure, or both. The air is evacuated through small vacuum channels, allowing the sheet to conform exactly to the mold surface.
This is a thermoforming mold for cups.
The part is shaped, it's rapidly cooled, using chilled air or water channels built into the mold. This locks in the final geometry and restores stiffness so the cup can hold its shape. Plug assist thermoforming uses a shape tool called a plug assist to mechanically drive the heated plastic sheet into the mold before vacuum is applied. Instead of relying solely on differential pressure to pull the material into place, the plug physically preforms the sheet and forces it into a controlled deformation path. The primary engineering value of a plug assist is improved material distribution. In deep draw or high aspect ratio geometries, an unsupported sheet can overstretch, leading to thin spots and localized mechanical weakness. By engaging the plug first, we pre-stretch the material in a more uniform way. This results in tighter thickness tolerances, more predictable strain profiles, in a stronger final part. A well-designed plug can also reduce common defects, enabling deeper draws, sharper features, and more consistent part quality. Anytime the geometry demands high precision or significant depth, the plug becomes a critical tool in achieving a reliable and repeatable process. The next major step is rim rolling, which gives each cup its smooth, rounded edge. First, the rim is preheated, a step called thermal conditioning. The edge is warmed to just below the polymer's glass transition temperature, Tg, where the material shifts from a stiff, glassy solid to a more flexible, viscoelastic state. At this temperature, the polymer's elastic modulus drops sharply, allowing it to bend without cracking. If the rim is too cool, it becomes brittle and can develop tiny fractures called crazing. These create the white, chalky edges known as stress whitening. But if the heating is right, the polymer chains can move and realign, giving a clear, smooth, and durable rim. Once the rim reaches its ideal temperature, the cup passes through a set of rotating rollers. These rollers, made of steel or ceramic, gradually curl the edge outward and upward, while a mandrel supports the cup from the inside. The result is the familiar rounded lip that adds strength and comfort when drinking. Temperature control here is critical. Too cool and the rim cracks, too hot and it loses shape. That's why modern systems use PID-controlled heaters to keep the temperature within just a few degrees of Tg. After rolling, the cup is cooled again using forced air or chilled mandrels to lock in the final shape. Each batch of cups goes through an automated quality inspection. Instead of checking every single part, machines use statistical sampling in vision systems to look for cracks, uneven curls, or surface flaws. If defects appear, the system can automatically flag or reject affected batches. Today's vision systems can catch even the smallest defects with impressive speed and precision. But there are also simpler, hands-on ways to check cup quality that don't require advanced machinery. Under polarized light, hidden stresses within a PET cup are revealed in vivid color. By placing the cup between two polarizing filters, light waves twist as they pass through strained regions, creating bright, shifting patterns called birefringence. These colors map the internal deformations, offering a clear visual signature of how the plastic was shaped under pressure. By examining these patterns, engineers can quickly identify areas of non-uniform draw, residual stress, or uneven forming, all without damaging the sample. After quality verification, attention shifts to material recovery. Each thermoformed sheet leaves behind a trimmed framework, known as the skeleton, which can account for a significant portion of the original material. Rather than being discarded, these skeletons, along with any off-spec parts, are automatically conveyed to the recycling system. The collected skeletons move directly into an industrial granulator, where high-speed rotating blades cut the material into uniform PET chips. Controlling the chip size is important here. Consistent geometry ensures stable feeding, predictable melting, and proper pressure development inside the extruder. After grinding, the regrind chips are blended with our selected ratio of virgin or post-consumer PET, depending on the production requirements. This blended material is metered into the extruder's feed throat, where the process of converting solid PET into new sheet begins. Inside the extruder, the chips are conveyed by the screw through a series of temperature-controlled zones. As they advance, the material experiences both heat and shear, gradually transitioning from solid particles into a fully molten, homogenized melt. Devolatilization ports help remove any remaining moisture or trapped gases, preventing degradation and ensuring optical and mechanical consistency in the final sheet. Before the material exits the extruder, it passes through a melt filtration system that captures fines, dust, or contaminants introduced during grinding. By the time the PET reaches the die, it's a clean, stable melt ready for precise sheet formation. At the extrusion die, the molten PET is forced through a narrow slit that defines the sheet's initial thickness and width. Immediately afterward, the sheet enters a chill roll stack, which rapidly cools and calibrates it. These rollers set the final gauge, surface finish, and overall dimensional accuracy. From there, the sheet is trimmed and rewound, ready to be fed back into the thermoforming line, closing the loop from web to chip to melt to new sheet. Once the recycled material is reprocessed into sheet stock, it's returned to the forming line, closing the loop within the production system. Meanwhile, on the main line, freshly trimmed and rim-rolled cups continue downstream. After trimming, the cups move into the packaging and distribution stages, the often overlooked final phase of production. Robotic stackers organize and count the cups, forming precise stacks ready for packing. These stacks are loaded into bags or cartons, which are sealed, labeled, and barcoded. Next, palletizing systems arrange the boxes into stable layers on pallets, using stretch wrap for secure transport. Automated guided vehicles or forklifts move them to staging areas for shipping. From there, products go to distribution centers, where they're sorted and shipped to retailers, restaurants. As automation and sustainability drive manufacturing forward, thermoforming shows how tradition and technology can coexist. Advances in tooling and simulation now allow engineers to predict material stretch, optimize cooling, and reduce setup time. Traditional materials like polystyrene and polypropylene remain common, But co-extruded and recycled blends are increasingly used where performance and sustainability must align. Analysts project that the global disposable cups market will reach roughly $22.14 billion by 2030, growing steadily from current levels. That forecast underlines how many millions or billions individually formed containers must roll off production lines each day, underscoring the ongoing economic weight and industrial importance of cup thermoforming. As sustainability and efficiency continue to guide modern manufacturing, the thermoforming process keeps evolving, becoming cleaner, smarter, and more circular than ever before. This is thermoforming, the art and science of shaping the future, one cup at a time.